Cauchy space theorem. Okay, so this is what we are going to discuss, and here, before going to some specific application, uh, let me introduce to you a special type of curves, like which some of you probably have seen before, and these kind of curves are interesting for the reason which I will explain. So the curve that I want to talk about, these are called Jordan curves. So what are Jordan curves? So of course we had taken smooth, piecewise smooth curves. So here Jordan curves are um, non-self-intersecting closed curves. Non-self-intersecting except for endpoints. Closed curves. Okay, so that means like any curve like this. So this kind of this is not allowed. Okay, so this kind of intersection, like it's not allowed. So in a way, you can say that this is an one-one function on let's say close 0, open 1. So it's not going to come back to any point. So these are the kind of functions that we have, like curves one takes often. So the nice property that these Jordan curves have is the following. So for example, for a Jordan curve gamma, C minus gamma has, like from the picture it should itself, it should be clear, exactly two components, two connected components. Okay, so one which is bounded and one unbounded. So that's again clear, like if I have some curve like this, then clearly there is one connected component of C minus gamma, which is the exterior of the region enclosed by gamma, and another one is the interior of the region enclosed by gamma. So these are the two connected components. Okay. So this one is that. So therefore, what happens is that hence uh, the winding number has only two possible values. Okay, so tell me what are the possible values in gamma A. So tell me what if A belongs to the unbounded component, then what happens?
0 and 1.
So in this case,
0.
in gamma A, this is 0. So that's already standard. Now if A belongs to bounded component, then what happens?
1.
Yeah, why it is 1?
Because A के अराउंड एक ही बार मूव कर रहा है, मतलब जो
So it's, yeah, it's winding around A exactly once, right? Because I have said it's non-self-intersecting. So like it's not allowed that I keep circling around a point again and again on the same path. So therefore, this winding number is 1. So this is what is going to be there. So means like of course here when where we take positively, one needs to be slightly careful, positively oriented. Okay, or if necessary, I'll put smooth as well, just so that the integration is fine. Smooth journey. Okay, so this is what we have, and in this particular case, our so for journey curve, for a smooth journey curve, gamma, the Cauchy residue theorem reads as integral of f over gamma is 2 pi I summation k from 1 to n residue of f at zk, where z1 to zk are the singularities of f encompassed by gamma. Okay, or the singularities, those are enclosed by gamma. Fine. So now that we have this, we are now going to define like this is one of the very simple case of Cauchy residue theorem, and often you will see that one uses Cauchy residue theorem in this form. Okay, of course here you need to know that your curve is a Jordan curve, or it's non self intersecting and all that. Okay, then only you can like immediately apply this form. Fine. Now, as I said, I'm going to look at Cauchy residue application of Cauchy residue theorem. So for that, I'm going to look at a particular type of singularity. I'll tell you for the fun, like why I'm more interested about that particular kind of singularity. So, for example, if you think of a removable singularity, then we have seen that removable singularity, for that the principal part is 0, and therefore the residue is 0, and hence as far as the integration is concerned, removable singularity, like uh, having removable singularity or not having any singularity, there is absolutely no difference as far as the integration is concerned. Of course, you need to get a holomorphic function, you need to just make your function to be continuous over there and all that. But as far as the integration is concerned, the value has, there is no change that way. Okay, so effectively, there is nothing as far as removable singularity is concerned. And now, if you think of essential singularity, then you really need your LoRa expansion to figure out the residue. So often these two types of singularities, like especially the essential one, are studied with limited interest. Okay. And because finding residue has no other option, right? Because for example, the formulas that I have given you for coefficient of LoRa expansion, those integrals also you might be difficult to evaluate and all of that. So therefore, you one might think of only considering, you know, points which are, or singular points which are not essential singularity, because for essential singularity we have no way to know about the residue other than looking at the LoRa expansion. Okay. So, of course, from that perspective, we see that essential singularities are not so interesting ones to deal with. That's number one. And number two is that, of course, I already explained that from the point of view of integration, having removable singularity or having no singularity has actually no difference. So therefore, we are going to especially look at functions where the singularity is a polar singularity. So we now focus on functions which are having polar singularities. Okay, so in this case, of course, I have given you formulas. Using that, you can calculate the residue. For example, if it is a simple pole, you can just multiply by s minus alpha, take the limit, you will get it. Or if you have higher order poles, by taking by multiplying suitable power and then taking derivative and so on and so forth, you can get this integral. Okay, so this is fine. There is absolutely no problem when you have polar singularity. So you have other ways to find the residue. Okay, so in the context of integration, therefore, these polar singularities are quite interesting. So you can do interesting things with them because you will get information about the residue much easily. Okay, so we are going to give a name for functions having only polar singularities. So here goes the definition. Let D be a domain. We say a function f on D is meromorphic if f is holomorphic on D except for an isolated set of points where f has polar singularities. Okay. So if we have that, then the function is called meromorphic function. So that means what? It's a holomorphic function, and except for finitely many points, or except for not finitely many, but some isolated set of points where the function is having singularity, and the singularities are polar singularity. So meromorphic function means it's a function with singularity, but those singular points, of course, they are going to be isolated, and these singular points are going to be polar singularities. Okay. So that's the definition for meromorphic. Like holomorphic, here we have notion of meromorphic, and this is often the set of meromorphic function on FD on D is denoted by, like holomorphic was denoted by HD, here we denote it by MD, meromorphic. So we will be mainly focusing on these kind of meromorphic functions. So let's see. Now comes the first um, application of Cauchy-Deschutes theorem. So is the definition clear of a meromorphic function? Yeah?
Yes, sir.
Okay, fine. So here goes the first application. This is called argument principle. So what's the statement? Let D be a closed curve domain. So closed curve domain, and gamma be a smooth Jordan curve. Of course, whenever I do not say anything specifically, I always say positively oriented. Let f be a meromorphic function, or let f belongs to MD, such that f has no zeros or poles on gamma. Let capital Z be the number of zeros of f counted with multiplicity, of course, and p be the number of poles of f, again counted with multiplicity. So that means, suppose I have a pole of order 5, I'm going to count it 5 times. Okay, so I'll say that there are 5 poles. Let's say I have only one pole with order 5. Similarly, if I have only 1 0 with order 7, I will say that I have 7 zeros, like that. Okay, so Z is the number of zeros of F, and P is the number of poles of F inside gamma. So this is happening, all these are happening inside gamma. So all these are happening, so all these poles and uh, zeros are lying inside gamma, or in the, you can say, the encompassed by gamma. So then it turns out 1 upon 2 pi I integral f prime over f is z minus p. Okay, so this is the statement of the argument principle. Of course, I will have to explain to you why this is called argument principle. Sorry, n is missing. What does this statement have to do anything to do with arguments and all? Okay, so this I need to explain. But let us try to understand what is the statement. Statement is saying that I have a monomorphic function, and then of course I have a smooth curve, which is such that like the function should not have any zeros or poles on that curve. And now z is, let's say, number of zeros of f, and p is the number of zeros of poles of f. Then 1 upon 2 pi I f prime upon f is equal to z minus p. So this one, of course, you can interpret as integral over gamma, or rewrite as 2 pi I into z minus p. Okay. Now, sorry, this is minus, not z minus. Okay, so now, of course, if you think of applying Cauchy residue theorem, you see you already have this 2 pi I over here, and clearly it was I have taken gamma to be a smooth Jordan curve, and in case of Jordan curve you saw that the winding number is just 1, so therefore the winding number does not feature. So therefore, from the statement itself, you should be able to tell me that on which function I should aim to apply the Cauchy residue theorem. What do you think? Tell me on which function should I aim to apply my Cauchy residue theorem? Yeah? Any guesses?
Any function which is differentiable.
No, no, no. In the context of argument theorem, and means proof of argument principle, in which function, for which function I should apply Cauchy residue theorem to get the proof?
F dash by F.
Exactly. So we are going to apply Cauchy residue theorem to the function f prime of f prime upon f. Apply Cauchy residue theorem. This is not Chinese remainder theorem, huh? Cauchy residue theorem on f prime upon f. Okay, so if I have to do that, I need to really understand what are the poles of this function which are encompassed by gamma. All of you agree to this? That to apply Cauchy residue theorem on this function, I need to know what are the poles of this function, or like what are the singularities of this function rather, which are encompassed by gamma. Agreed?
Yes.
Yes. Now, as it turns out that this function f prime upon f. So tell me in which of the ways you can get singularity of this function f prime upon f. Just imagine and tell me on which points you can have any kind of singularities for this particular function f prime upon f.
Zeros of f are those
Yeah,
false.
clearly zeros of f are those points where the denominator will not make sense. So therefore, I will have singularities. And any other points other than that?
No, sir.
Nothing else. What do you think about poles of f? What do you think about poles of f?
False of f are zeros of this function.
No, no, no. They are not zeros of this function. But you see, first of all, the denominator does not make sense when you take a zero of f. You agreed. Now, if I take a pole of f, then the numerator does not make sense, right? Isn't it? Is it clear what I'm
Yes.
saying? So therefore,
Yes, sir.
problematic points. So I am not calling singularities them, but at this moment, problematic points are zeros of f and poles of f. All of you agree to this? That except for these points, in all other points, I have absolutely no trouble. Right?
Yes, sir.
Agreed or not?
Yes, sir.
Now let us look at a zero. Okay, so let alpha be a zero of f of order k. So I'm taking this alpha to be a zero of order k. So then if I write down the power series expansion of f around alpha, then how does it look like? F of z is equal to, tell me where does it start from?
1 upon my z to the power alpha, 1 upon my z minus alpha to the power k.
No, no, this is a zero. Be careful.
A minus K.
Sorry.
Right.
So it starts from
Z minus alpha.
z minus alpha power k. Order is k given, right? So let's say ak, this one, plus 1 z minus alpha power k plus 1, so on and so forth. All of you agree to that? So
Yes.
around alpha, I have this. So I can take out z minus alpha power k common and times some gz, which is such that g is holomorphic on holomorphic around alpha. Fine, if g is holomorphic around alpha, that's good. Now moreover, g is not g alpha is not equal to 0. So I have taken out all the powers, all the zeros away. Okay, so here I can write ak is not equal to 0. Okay, great. I have this one. Now you just look at this that once I have this, what can I say about f prime? F prime of z is z minus alpha power k g prime of z plus k z minus alpha prime power k minus 1 g of z. That's easy in a neighbor around alpha. So around alpha, what is f prime z divided by f of z? What is it coming out to be? Tell me, what is it coming out to be? Yeah, 1 upon, it's coming out to be k upon z minus alpha. Come on, this you should be able to do. And then g prime z divided by gz. All of you agree to that?
Yes, sir.
Okay, so now around alpha, what can you tell about this function? G prime upon g.
Holomorphic.
This is holomorphic because g of alpha is
Not equals to 0.
not equal to 0. So this guy is holomorphic around alpha, and there is another part. So what about this particular part? What can you say about this part? How does this function behave around alpha?
Simple pole.
It has a simple pole. What is the residue?
K.
Equal. Since g of alpha is not equal to 0, g prime z divided by gz is holomorphic around alpha, and hence f prime z upon f of z has a simple pole at alpha with residue k. All of you agree to this?
Yes, sir.
So
Yes, sir.
that shows that if I start with a 0 of f, it's going to have a simple f prime upon f is going to have a simple pole at that point, and the order of the 0 is getting reflected in the residue. Okay? So this residue is k, which is positive in this case because number of zeros, order of 0 is positive. So that's what we are getting. Fine, all good. Now let's do it in case of pole. Okay, fine. In case if alpha is a pole of f of order k, then tell me what can I write? Then around alpha, what can I? How can I write f? F of z will look like
A minus
Cz
K.
upon z minus alpha to the power k.
that's one step ahead. But like if somebody has not understood that, let me write it as h. G I have used z minus alpha power k. Why is this? Because the LoRa expansion will start from a minus k, z minus alpha power k, so on and so forth. A minus 1 divided by z minus alpha plus a naught plus a1 z minus alpha plus dot dot dot. Okay, so you take out z minus alpha power k and you get a power series where h is holomorphic around alpha. And tell me what is the value of h at alpha? H of alpha is equal to what?
Non-zero.
What is the value
A
precisely?
minus k.
A minus
A
K.
minus k.
Minus k, and hence not equal to 0. Very good. So you see, here I have z minus alpha power k times gz. Here I have hz divided by z minus alpha power k. So almost quite close to each other. Okay, so therefore what is f prime? F prime is, again, I can see that this is h prime z divided by z minus alpha power k minus k hz divided by z minus alpha power k plus 1. Okay, so this is of course except around alpha, except alpha. So except alpha, I'm doing this. So f prime upon f, what is this function? F prime upon f. This function, this time, what am I getting? F prime upon f. Tell me.
Upon my HZ
H prime z divided by hz, and then
minus K upon my Z minus alpha.
minus k upon z minus alpha. So you can tell me what can I say about this? It's
This
around
one is holomorphic.
this one is holomorphic again because h of alpha is not
Not
equal. And what can I say about this guy?
simple pole that with residue K minus K.
Yeah, simple pole with residue minus k. All of you agree to this? Yeah.
Yes, sir.
So hence, in this particular case, f prime z, actually I should have probably written beta, but doesn't matter, you understand, has a simple pole at alpha of with residue minus k. So therefore you see, it does not really matter if you have is whether you have a zero or a pole. Whatever is your whatever is the status of your whether you take a zero of f or a pole of f, you are going to get that f prime upon f is going to have always a simple pole at those points. Only difference is going to come at the level of residue. If you start with a zero, the residue is going to come as positive, namely the order of the zero. And if you start with the pole, the residue is going to come out to be negative, and that's going to be minus of the order of the pole. Is this clear to everybody? Yes?
Yes, sir.
And
Yes.
once we are done with this, do we get the proof of argument principle? What does it say? This integral is going to be 2 pi I times z minus p. And Cauchy residue theorem says what? Cauchy residue theorem says integral of gamma of f prime over f, integral of f prime divided by f over gamma is 2 pi I times sum of the residues, because here my gamma is a smooth Jordan curve. Sum of the residues. And here, what are the residues that I am getting? If I start with a 0, I am getting the residue is coming out to be the order of the 0. So if I sum all of them, I am going to get total number of zeros counted with multiplicity. And if I take a pole, I see that the residue is coming out to be minus of the order of the pole. And so when I sum all of them up, I am going to get minus total number of poles counted with multiplicity. So is this clear to everybody?
Yes, sir.
Yeah. So hence integral of f prime over f by gamma is 2 pi I times z minus p by Cauchy residue theorem. Okay, so this is what is the content of argument principle, and the proof is just a very simple application of Cauchy residue theorem. Okay, so remember here that what we saw is that if you start with a 0 or a pole, this logarithmic derivative, which is f prime upon f, this will always have a simple pole at that particular point. Okay. Only difference is that whether it's how will you understand that this pole is coming from a 0 or a pole. You will not get it from the residue. If the residue is positive, then the singularity is coming from a 0. If the residue is negative, then the singularity is coming from a pole. Okay, so that's the crux of the matter. Okay, fine. Now, I need to tell you how you can, like, why is it called argument principle? Okay, so why do we have such a name? So why do we call it argument principle? Okay, so here like I have already told you, this f prime upon f is called the logarithmic derivative. Okay. So that means what? You need to take log of f. Of course, your f has to f should not vanish. Then only you can take log. And then if you take derivative, then that's going to be derivative of log of f is going to be f prime upon f. Okay. So therefore, first of all, try to observe the following. So let us write it down. Okay, so I have we assumed that f has no zeros or poles on no zeros or poles on gamma. So this was given to us, and we wanted to, once we have this, we wanted to say that, like, we wanted to understand the integral f prime over f. So I told you, of course, since f has no zeros, so log of f, I can consider log of f there. Okay, and this is the logarithmic derivative. Okay, but nevertheless, let's write down what is this integral: 1 over 2 pi I over gamma f prime over f. So this one, let's say gamma is from closed interval 0 to 1, then this is 2 pi I integral from 0 to 1 f prime of gamma t divided by f of gamma t, and then gamma prime t dt. Okay, this is precisely I have. Now notice this one, that this I can actually write 1 over 2 pi I 0 to 1. Denominator is f composed gamma of t dt. And what can I say about the numerator?
F compose gamma prime t.
F composed gamma prime t. This is coming from
Chain rule.
chain rule, right? Okay. Now, what did I say? That this guy is this f whatever the function. This is now f composed gamma prime divided by f composed gamma, and this, as I said, this has a primitive which is log, right? So log of this thing, when you take log of f composed gamma, and if you think of its derivative, it's going to be f composed gamma prime divided by f composed gamma. So this has a primitive which is log. So therefore, this integral is nothing but 1 upon 2 pi I. This integral is nothing but 1 upon 2 pi I log of f of gamma 1 minus log of gamma 0. Okay. This is precisely what I get. Okay, fine. That's all good. Now, let's observe certain things. I have gamma 1 is equal to gamma 0. That's fine. So therefore, f of gamma 1, gamma is a closed curve. So f of gamma 1 will be f of gamma 0. That's fine. Now the point is here, log, of course, these two are equal as numbers. So I might be very tempted to say that, therefore, log of f of gamma 1 minus log of f of gamma 0, this whole thing should be equal to 0. This I'll be very tempted to, but that might not be the case. Yeah, because you see, we have seen that it completely depends how, means what do I have as my argument at f of gamma at 0 or f of gamma at 1. Of course, these are the same points. Like, for example, if I think of, like, our principal argument was starting from minus pi to going, starting from minus pi to going up to plus pi. Of course, you can say that the minus one has, like, this can have several different. There will be several ways of representing its argument, right? So e power minus I pi, this number is same as e power I pi. Okay. So therefore, when taking log, one needs to be slightly careful. Okay, so one needs to take into account what is going on over here. Okay, so fine, let's do that. Let's take care of that as well. Okay, so here, this is what we need to be careful. We do not write like this directly. Okay, now imagine, as I said, log of this one might not be equal to log of that, because what is log z? Log z is actually equal to log of mod z plus I times argument z. Okay. So therefore, when I think of this thing, so of course these two numbers are equal as numbers, so their absolute value is going to be equal. And of course when you think of absolute value, that's a non-negative, not means like if these numbers are all non-zero numbers. So for all of them, the real logarithm, what is there in real line, that logarithm is a fixed value, and change is in the argument. Okay, so this implies log of f of gamma 1 minus log of f of gamma 0 f of gamma 0. This difference is nothing but actually log of mod of f of gamma 1 plus I times argument of f of gamma 1 minus log of mod of f of gamma 0 minus argument of f of gamma 0. Okay, 1, 2, 3, that should have another bracket. Now this guy, of course, I know f of gamma 1 is equal to f of gamma 0. So as complex number, they are same. So when their modulus you take, they are the same real positive real number. So their log are like the real logarithm is the same. So you can cancel this. And therefore, what I effectively have, this difference is nothing but I times argument of f of gamma at 1 minus argument of f of gamma at 0. Okay, so 1 upon 2 pi I integral f prime over f over gamma is nothing but 1 upon 2 pi argument of f of gamma of 1 minus argument of f of gamma of 0. Okay, so this is the difference between these two things, and thereby it's called the argument principle. So you see, of course, you know that since f of gamma of 1 and f of gamma of 0, they are the same number, but you are traveling, you started traveling at point 0, and then you came back. So this is a closed curve, right? Gamma is a closed curve. So when you just look at this composition, f composed gamma, so that is also that gives you a closed curve. So it comes back to the same point. That's correct, but it's going around and then coming back to that point. So therefore, there is a change of argument, and we know that when I start from somewhere and in complex plane and I go around somehow, especially when I, somehow, let's say I was in the upper half plane and then I went to lower half plane and then I came back. For this kind of scenarios, it's evident that I will gain some more argument in this process of going around. And of course, since these are the same points, this argument, change in argument is just going to be some integer multiple of 2 pi, and there is a 2 pi divided. So when you cancel, that's going to give you an integer k. And of course, by argument principle, you know what is this integer? This integer is z minus p. So z is number of poles, zeros counted with multiplicity. P is number of poles counted with multiplicity. So this integral 1 upon 2 pi I is f prime upon f, which is given by z minus p by argument principle. This actually captures the difference of the argument f of gamma 1 uh, and f of gamma 0. Okay, so you had started at a particular complex number f of gamma 0, and you came back after going around by means of your gamma and your f, came back to the same point. But even if we come back to the same point, we will gain some argument. So for example, just a simple diagram, I can start from 0. 0, let's say, has argument 0, and then I go around and first of all I come back once, and then I go around again and come back another time. If I keep doing things like this, I will be coming back to the same point, but I will be keep adding some arguments. Right? Okay. So therefore, this difference, what is this difference happening? That is captured over here, and this is what why statement is called argument principle. So because this is talking about, this integral is actually talking about this difference in argument, and that argument, like the difference in argument is getting captured by the number of zeros minus the number of poles counted with multiplicity. Is this clear to everybody?
Yes, so
Yeah. Okay, great. Yeah.
if we don't use the binding number concept, then it will 0.
Sorry.
If we didn't use the binding number concept, like we start from 0 and again come back to that. So the argument of f of r0, f of r0 is 0 and f of r1 is 1. R1 is 2 pi, okay, by the binding number concept.
So here I am not talking about binding number for the following reason. I have anyway taken gamma to be a simple curve, simple like Jordan curve. So that's going to wind only once. That's fine. But you do not know, even if your gamma winds only once, what does f do to that? Right? Once you apply f, it can very well happen that you wind around 0 so many times. Is it clear what I'm trying to say? So like it may so happen that your f is such a function that even without, let's say, completing a full circle around 0, like you started from gamma 0 and then you have gamma 1, so that's the closed curve, and on that you are like you are going to compose f. So it might so happen that even without going up to, like, you start at 0, but even without going up to 1, it may so happen that your f composed gamma has already become closed. Okay, so it might take so many turns, we do not know, and depending on the turns that it takes, of course this argument is going to change. Okay, fine. Is this clear? So here, to start with, we have taken gamma to be a simple Jordan curve. So there is like it's going to go around only once, but once you apply this f, you do not know how it changes. That depends on f. Fine.
Yeah, yes.
Okay, and like you absolutely said, this is what is actually the winding number, exactly what you have sensed, because here, like I said, of course, gamma is probably we are seeing it in a simple form, but this is actually the winding number, because I can say in the following way. So let me write down. It's good that you mentioned. So remark the integral should be very true. 1 upon 2 pi I f prime upon f over gamma can also be seen exactly because I was drawing this picture, right? That it started from here, went like this, and then went like this, and all that. So, of course, there is some kind of winding philosophy. So, it can be seen as winding number of f composed gamma around 0. That's true. This is what you were trying to say, Abhishek.
Yes, sir.
So here, how do we define winding number? So define, if you remember, the winding number was integral 1 upon 2 pi I integral of 1 over z minus a. Okay, so recall uh, the definition. Of course, from the picture, it's clear that that's the winding number, but let us do it rigorously. Recall the definition of winding number first. Winding number of any curve, let's say, okay, curve, let's say rho around 0. What is that? It's 1 upon 2 pi I integral over rho 1 upon z minus a. So here a is 0, so 1 upon z. So this is 1 upon 2 pi I integral from 0 to 1 rho prime t divided by rho t dt. Okay. This is precisely f of gamma prime t dt. So therefore now what do I have? We have just seen 1 upon 2 pi I integral over gamma f prime upon f is nothing but 1 upon 2 pi I integral from 0 to 1 f compose gamma whole prime t divided by f compose gamma t dt, and that should be, so this is n rho 0 is defined by this. So this guy is therefore nothing but n f compose gamma. Absolutely, that's the. So although gamma is having winding number 1, your f could result in having, like, it might give you more winding number, and that is precisely uh, what is getting captured over here. So this is the winding number. Good observation. Okay, fine. Now that we have this, I'm going to do one final application for today, and then we will see application of these applications, and then so the next theorem that I'm going to prove is called Rouché's theorem. Okay, so this is a very powerful theorem. I will of course give you some more exercises on this, and we will see how to use this Rouché's theorem while discussing applications of these things. Okay, so what is Rouché's theorem? So let f g be holomorphic functions in a closed curve domain. Okay, so I have a closed curve domain D, and I have f and g holomorphic functions there. Let gamma be a smooth Jordan curve. Suppose I have a smooth Jordan curve. Now I am going to put some condition on f and g. So if mod of f of z is bigger than mod of g of z for all z in gamma, okay, then what I can say, then the number of zeros. So remember here f and g, these are all holomorphic functions. Okay, so this move towards curve only. So therefore these functions, there is no singularity at this moment. I am only talking about holomorphic function. So if mod of f is strictly bigger than mod of g for all z in gamma, then the number of zeros of f plus g encircled by gamma is same as the number of zeros of f encircled by gamma. Okay, so that means what it's saying, that if I have some superior function, then you imagine f plus g, and you are just going to get the same number of zeros which is given by the superior function. Okay, so you can think of, like, just imagine the polynomial z power n, so that z power n is having n many zeros, all of them are at 0, and let's say I can figure out some, like I have already told you that for example, when you take polynomials, the growth of the polynomial is determined by the leading term. So if the leading term is of degree n, then of course that leading term is going to determine how the polynomial is going to grow. So there will be certain circles. You will get definitely some circle where, for instance, all the highest degree term is going to dominate all the lower degree terms. And once that happens, once this domination happens, then you can apply Rushi's theorem, and then you will get that within that circle, your function is going to have n many zeros, and of course you can take larger and larger circles, and you will get that a polynomial of degree n will have at most n zeros. So in fact, exactly n zeros in that, because z power n has n zeros. Yeah, so these kind of applications are these kind of statements that one gets as an application of Roussell's theorem. So whenever you need to find out zeros of certain functions, so what you do is that you try to understand what is the central part of that function, try to collect that, and then try to show in a way that for some on some circle, let's say, that main component is going to dominate all other remaining components as far as the modulus is concerned. And once that happens, then if you want to find out the number of zeros, all it matters is that you figure out what are the number of zeros of the main component. So this is precisely how Roussell's theorem works. Okay, so of course we will see some more examples. Yeah. Fine. So this is precisely I have, and now let's go to the proof of Roussell's theorem. So here, of course, I am going to use argument principle, but we need to be slightly careful. Okay. So, like I said, I'm going to use argument principle. So, of course, I have to somehow, of course, here I don't have any poles, but effectively I need to show that zeros of, so we show z of f plus g is equal to z of f, where z of f plus g and z of f denote the number of zeros in T of f plus g comma f encircled diagram. Okay, so of course I need to get hold of these quantities. Since I need to get hold of these quantities, it's natural that I will be considering integration of the form f plus g prime divided by f plus g, and I will also be looking at integral of the form f prime divided by f over gamma. These two integrals I am going to take. That's very natural. And of course, I have taken holomorphic function, so there is no poles, no poles are coming. So the only singularities of f plus g or f prime upon g, they're going to come from zeros of f and g. Okay, so that's for this purpose. This considering these two integrals, that's immediate. Okay, so fine. Now that I have to take f plus g prime divided by f plus g, f prime divided by f, let us try to understand their relation. Okay, so for this, write f plus g is equal to f into 1 plus g by f. So this is how I'm going to write my f plus g as, and it's a very simple observation, so that note a, let's say I have az equal to bz into cz or holomorphic functions a b c, then I get a prime z divided by az is nothing but b prime z divided by bz plus c prime z divided by cz, right? Wherever this a is non-vanishing, so wherever a is not equal to 0. Fine, I get this, right? Or you can just take logarithm and then take derivative. This is what we get. Correct? All of you agree to that?
Yes, sir.
So
Yes.
therefore, I just need to have this. Like I will apply this for this one. Now here, first of all, as I said, I need a to be non-zero. So that let us observe that f is non-zero, and f is going to be non-zero because I can just clearly see that mod of f is bigger than mod of g, which is bigger than or equal to 0. So clearly your f is non-vanishing on gamma. Okay, so clearly f is non-vanishing on gamma as mod of f z is strictly bigger. So remember, this one is a strict inequality. It's strictly bigger than mod of gz, which is of course bigger than or equal to 0. So f is non-vanishing, of course, therefore you can consider g by f on gamma, that's going to be holomorphic. 1 plus g by f, that's also going to be holomorphic, and it's going to be non-vanishing because g mod g is strictly less than mod f on gamma. So this guy is non-vanishing, this guy is non-vanishing, of course f plus g is going to be non-vanishing, no way. So therefore what I get is that all these functions in non-vanishing, they are holomorphic. Okay, so we get f plus g f 1 plus g by f, all are non-vanishing on gamma. Okay, so therefore I know, so we have f plus g prime divided by f plus g is equal to f prime by f plus 1 plus g by f prime divided by 1 plus g by f. This is what I get. So therefore, if I integrate, this implies integral 1 upon 2 pi I integral over gamma f plus g prime divided by f plus g is equal to 1 upon 2 pi I integral over gamma f prime upon f plus 1 upon 2 pi I integral gamma 1 plus g by f prime divided by 1 plus g by f. Very nice. This is what I need to take care of. So the left hand side over here, this guy is z of f plus g. There is no pole, of course, in this case because my functions are holomorphic. The right hand side is z of f plus 1 upon 2 pi I integral over gamma 1 plus g by f prime divided by 1 plus g by f. Okay, this is what I have. And now to understand what is this integral is, I can write that this is integral of, this is nothing but the winding number of h composed gamma of 0 where h is 1 plus g by f. All of you agree to that? This is precisely what I have written here in the remark, which Abhishek was mentioning, that this integral 1 upon 2 pi I f prime over f of gamma is nothing but the winding number of f composed gamma around 0. All of you agree to this? So therefore, this integral becomes in the winding number of h composed gamma around 0, where h is 1 plus g by f. Fine?
Yes, sir.
Okay, great. So now let us try to understand what is happening with h composed gamma if h is 1 plus g over f. What is this happening? Whether I get some contribution coming from this winding number. Okay. So ideally, what you would like to show, of course, this whole thing is the winding number. Ideally, you would like to show this winding number is 0. Okay. So let us see if this winding number is indeed 0 or not. Okay. So note, mod of f of z is given to be strictly bigger than mod of g of z on gamma. So that's given. So this implies what? Mod of g of z divided by f of z is strictly less than 1 on gamma. Okay. So therefore, you can say hence on gamma this quantity is strictly less than 1. And what is h of z? H of z is 1 plus gz plus hz. So with 1 you are adding something which is having absolute value less than 1. So this h function on gamma, remember all these are happening on gamma. So on gamma, this h function does not even go close to 0. Okay. So of course this h composed gamma is going to be a closed curve, that but somehow it does not encompass 0 at all, because it's not even possible. Why? Because hence on gamma h is equal to this, and thus takes values on the ball b1 1. So 1 is the center and another one is the radius. Okay, so therefore what I have, let's say this is my 1, and you just imagine a ball of radius 1 around 1, and what happens, your h composed gamma, is somewhere here. Okay, is encircling 1 perhaps, but it's within this range. It lies within 1 distance from 1, this h composed gamma. It might not encircle 1, that's a different matter. It stays at most in 1 distance from 1. Okay, so this is what is the picture of h composed gamma. Fine. Now clearly 0 belongs to the unbounded connected component. 0 belongs to the unbounded connected component of C minus H composed gamma. Okay, so it's clear from this picture that this 0, if you think of the connected components of C minus H composed gamma, then 0 belongs to the unbounded connected component, and hence what can I say about the winding number? Composed gamma of 0. What is this winding number?
0.
This winding number is 0, and that is precisely gives us, like, once this winding number is 0, what do we get? Hence we get so we get z of f plus g is equal to z of f. Okay, so that completes the proof of Cauchy's theorem. Okay. We will today I have few minutes extra, but I will still not do anything anymore. I will do some applications in the next class. I'll give some tutorials and do some applications of this Cauchy's theorem and argument principle, because precisely this is what I thought I will keep for the syllabus in quiz. Okay, and so therefore today I don't want to do anything. I will give, of course, another tutorial sheet, some problem sheet, where you can do some problems based on these things. Also I will do some applications maybe in the next class, and of course Thursday we are having the quiz. Okay, so here, like I said, the important understanding that you need to take is that this argument principle can be, the argument, the whatever the integral in the argument principle, it it tells you about the difference of the, it tells you the difference of the argument at a composed gamma at 1 and at 0, and thereby this is nothing but actually the winding number of a composed gamma around 0, and this is precisely used in the proof of Cauchy's theorem, which is a very powerful tool to understand about the number of zeros of certain functions. Okay, so we will have, like, once you get these kind of comparing inequalities, you will be able to use Cauchy's theorem to talk about number of zeros of certain function from your knowledge about zeros of some known function. So this is what is the content of Cauchy's theorem, and like I said, some of the applications of Cauchy residue theorem. Okay, so I'll stop here for today, and in the next class, we are going to, like I said, discuss some more of these kind of applications. Okay, so you will see, like I said, this Cauchy residue theorem is a very powerful statement, and lot of important information can be actually derived from that. Okay, so of course we started by deriving the argument principle, and slowly we showed how argument principle led to this understanding of difference in argument, followed by understanding this integral in terms of some winding number, and eventually it gives you the Cauchy's theorem. We will see more of that in the next class, and I stop here, so you can tell me if there are any questions.